Okay, what was the absolute maximum of that function?
21.
What is it? 21. What was the absolute minimum? -6.
What's the proper way to notate that?
Pardon me?
Like, what's the proper way to notate that? Like,
Just put maximum minimum.
but just 21? You
Yep.
don't need the X value?
You don't need it. Now, I always think it's good to have it because then you know where it happened, but if they're asking for the maximum value of the function, they just want the y coordinate. That's all they want. All right. Moving right along. Oh, where's my mouse? I forgot my mouse. Oh, well. Oh, no, I didn't. Okay. There we go. So before we start, I have something mathematical related to mathematics, but not anything to do with our course per se. No. Still, yeah, I don't want to talk about that right now. Okay, so this is a, how do I say this? This is a mathematical problem, okay? It's a problem, it's out there, anyone can try and solve it. If someone was able to come up with a solution to this problem, then the world as we know it would change immediately. So let me explain what the problem is. This has to do with cryptography. You know what cryptography is? Yeah. It's basically the idea is that since the beginning of time, humans have tried to send messages to one another without other people being able to intercept the message and know what it is, right? So we come up with different codes and things like that. And there's always been a battle back and forth between the people who are creating the codes and the people who are trying to break the codes, right? And sometimes the people who are writing the codes have the advantage, and sometimes the people who are trying to break the codes have the advantage. Right now, the people who are writing the codes have the advantage. And nobody has been able to break the code makers, all right? And I'm going to show you how they do it, and then maybe you'll see what I'm talking about, what the mathematical problem is.
Does this follow the basis of the Turing project?
The what?
I think his name is William Turing.
Turing? I don't think Turing has anything to do with this particular thing. I mean, Turing is like the father of computers, but... Okay, so let me get to the problem. So let's say that I'm trying to send a message, okay, to somebody over here, right? I'm trying to send my message out to them, right? So I'm trying to get some information from this person, this person. Obviously we can't yell the message out, because if we yell the message out, anyone could hear it, right? So the way currently it works is this. Like everyone's typed up an email or got signed on to their banking website or something like that, and it says it's encrypted, right? And depending on, like right now, iPhones, right? I've heard like iPhones, like the FBI, the NSA can't break into an iPhone. Have you heard that before? Do you believe that they can't?
They can.
Or do you think they can?
They can.
They can? Like legally, do they have the right to?
They don't like they do that legally, but illegally they can. But they are showing like that they can't do this.
What makes you think that?
Like
You just believe the NSA that much?
I have some research. Yeah, if you read the WikiLeaks, the Snowden documentary, so you can find how they are doing this.
Okay, so there's probably a way that they can get into the phone, but it's not by breaking the encryption. Yeah, they're not breaking the encryption. They're just finding like a back door into the phone. So let me explain the encryption. All right. So again, we're sitting here with this message we're trying to get from here to here, right? Okay. So stand by on that. I'm going to put a number up here. Okay, that right there is what we call a composite number. It's called a composite number because it is made up of two numbers that are prime numbers, right? 3 times 5. These are prime, which means that the only numbers that divide into those are itself and 1, right? So that's a composite. This is made up of two primes. Got me? Okay, so here's how the encryption that we currently use that's very powerful works. This person sitting over here, waiting for the message, yells out to this one. Now, they don't yell, but they do it electronically. They yell out the number 15, okay? So 15, and anyone out there in the world can see 15. Okay, so this guy over here says, oh, 15 is his number, is his magic number. It's called the public key, okay? That's what it's called. They get that number 15, and then they take their message, and they use that number 15 to scramble their message. So I'm not going to get into the details of how you do that, but there's a way that if someone gives you a number, you can use it to scramble your letters. So like maybe your A becomes a C, and all your B, becomes an H, and there's a way to take your letters from your message, scramble them using that number 15, okay? And then what you do is you yell back to them your scrambled message. You yell it, it's all scrambled, and anyone can hear it. So when it gets to this person, the only way to break the code, the only way to unscramble it, is to know that 15 came from 3 times 5. So if this person here, anyone who catches that message, if they know that 15 was 3 times 5, then they can unscramble it. Does that make sense? So it doesn't seem that hard, right? Except that's not what they do over here, okay? This person does not yell out 15. What they do is they start out with 2 prime numbers, all right? And the 2 prime numbers that they use are usually, depending on how powerful you want the encryption to be, these 2 numbers that they use are usually 40 digits long. 40 digits long. So when it comes to prime numbers, we know you can list them out, right? So like 1, 2, 3, 5, 7, 9, all the, I almost said 9, 11, right? All the prime numbers. That list of prime numbers goes on forever, right? There's no stopping to it. There are an infinite number of prime numbers. So they go and they are able to find 2 prime numbers that are 40 digits long. Then they multiply them together to create about an 80-digit number. And then they yell out, that's the public key, okay? This 80-digit number. And then they scramble the message using that 80-digit number. And then everybody sees it. Everyone knows the 80-digit number, but the only way to break the code is if you can take that 80-digit number back to its 2 primes. Now that may not seem like that's that big of a deal, but it's very difficult. If I just throw a number up here and ask you to find the 2 primes it came from, you would have an easy time if I gave you some small numbers. But if I gave you an 80-digit, it would be not only hard for you to do, it would be hard for a computer to do. So hard, in fact, that the number of digits right here that they choose is dependent on the technology and like how far computers have come. So let me try and explain this. If you were trying to make this safe in the 1980s, you could use some very small numbers, maybe some 10-digit, and the computers in the 80s wouldn't have trouble with that. But nowadays, you have faster computers and everything else, right? So you use larger numbers. So the people who came up with this encryption, it's called RSA encryption. These are the last names of the guys who came up with it, who get credit for it at least. The standard that they used to figure out how many digits to use here to make this unbreakable is they said, okay, let's just take the computing power in the world right now. Imagine that you put every computer on the planet trying to break that number. Then we want it to take 10 times the age of the universe for that to happen. That's the standard that they use for picking how big these numbers are. So computers get faster, right? Faster, we just go with bigger digits. I mean, now, could a computer stumble upon it? Maybe. Maybe, but it's nearly impossible. Was there a question? Yes.
Isn't that trying to be solved with quantum computing?
Well, quantum computing is what we think is going to be the next big leap. And that's because right now all computers kind of can only do like on and off. Quantum computing is trying to get basically more where you can do more than just on off. So you can really speed up the process of checking, right? This. So if someone could find some clean, simple algorithm to break a composite number down into its primes, now a large composite, then what would happen? Everything becomes insecure. Everything is no longer secure, right? Like your banking information, all that stuff, everything is all, now the code breakers have the advantage. So I don't see it happening anytime soon, all right? And it used to be, I don't know if this is still the case, when I first was researching this or reading about it, there's a program, a computer program that does that RSA encryption. And when I was learning about this, it said that if you were to take that program and put it like on a flash drive and like try and leave the country with it, that they consider that transportation or transporting a munition. A munition, yeah. So crazy stuff. Anyway, yes?
I know this doesn't relate to it, but like, so is this something that only the U.S. has, or that came up?
Oh, no. No,
Like,
this is out there.
Well, like who came up with it? Like what country?
I'm not sure where those guys were from, RSA. I don't think they're all from the United States, or, you know, I don't know the breakup. And I believe there's a guy that actually should be getting credit that was before them. They just kind of put all the work together into one like cohesive paper. But everyone uses it. So you hear about like these, I know a couple of years ago we were hearing about like terrorists that are using these apps to communicate with one another, you know, and the FBI can't do anything about it. Like when you hear that on the news, like don't believe that the CIA or NSA has some secret like way of breaking code. Like RSA encryption is super tight. You know what I mean? Like you're up against something there, okay? All right, so why did I talk about that? I have no idea. No, I was watching a little video. Have any of y'all ever heard of the Enigma machine used during World War II? The Germans came up with a code breaking machine, or sorry, a code generating machine. There's a video I was watching on it, and anyway, that we found a way to break that. But now with RSA encryption, there's really not much we can do. All right, we're moving on. So I hope you remember that when we were talking about chapter 4, we said that we were going to skip 4.2. Remember that? I said I'm going to come back to that. So moving on to 4.3. So derivatives in the shapes of graphs. So we have a lot of notes here, and a lot of this is pretty visual, so that's good. So our first definition here, or set of definitions, has to do with what's called increasing, decreasing, or constant tests. So if somebody gives you a function, all right, they give you a function, like I gave you a function on the test, on the quiz. Somebody hands you a function. If the derivative of that function is positive, greater than 0, on some interval, then the function must be increasing. So what does it mean for a function to increase again? What does it mean to say a function increases? So look at that function right there. That function is an increasing function, isn't it? Because as you move from left to right, the function goes up the whole time, doesn't it? So that is an increasing function. The first note is telling us that everywhere on that graph, when we look at the slope of the tangent line, it should be positive, shouldn't it? If the function is increasing, then our slope of our tangent line should always be positive. In fact, anywhere, any interval at any part of the graph or any part of the function where our derivative is positive, we are guaranteed it will be going up from left to right. Okay? The second part says anywhere that the derivative is negative, then the function will be decreasing, so it's going to be going down. And then anywhere where the derivative is 0, we will have to be flattened out. So that's increasing. That's what decreasing looks like. And again, if you look at the derivatives, notice they're all negative there, right? Slope of tangent line is negative. And then a constant function, of course, the slope of the tangent line is flat the whole time. Okay, pretty simple concept. Nothing crazy there? Okay. So look at this function. As we move from left to right, it increases, right? That means my derivative is positive. Right now I actually have the computer calculating it. The derivative right here is 24. So the slope of that tangent line is 24. That's positive, greater than 0. So I'm increasing. As I move, it's going to be increasing until I get to the top. Then what's it going to be? 0. Just right there at 0. Then I'm going to be decreasing until I get to there, 0 again, and then increasing, right? So when we talk about intervals, let me back this up. Okay, it's hard to tell maybe from where you're sitting, but can you tell the x value where this thing was 0? Can you tell what that is? Does that look like -3 to you? So would you agree with this? My function f that I'm looking at here is increasing. I'm going to use a little arrow next to f to represent increasing instead of writing the word f is increasing on the interval -∞ to -3. So I'm assuming that this arrow like continues to go down like that. So when I say -∞, I mean if I was to imagine myself coming in from way out here, it looks like I'm coming up, right, increasing the whole time until I get to an x value of -3, and that's where I stop increasing. Agreed? Is there anywhere else I'm increasing? Well, right here, right? At this point from here on, I'm increasing also, right? So what I need to include another interval with this. I need to go from 2 on, right? So the way I do that is I use the union symbol, and then I say 2 to infinity. See that notation? Okay, where is f decreasing? Yeah, between those two, right? So -3 to a +2. Okay? Where is f flat, or I should say, constant here? I'll just... Where is that happening? At -3 and +2, right? But those aren't intervals, those are points, aren't they? So the way you distinguish between an interval and a point is this. You use a brace instead. -3, 2. This means the point -3 and the point 2, or the x value, -3 and +2. All right? And that leads us to the first derivative test. We will use this a lot. The first derivative test says, suppose that you have a critical number of a function. Remember what a critical number is, right? Critical number is anywhere where the derivative is 0 or the derivative doesn't exist. So let's say that you're sitting there at some place where the derivative is either 0 or doesn't exist. Then, if the derivative changes from positive to negative at c, then you must have a local maximum at c. So the way I like to visualize this is like this. Let's say I'm looking at a graph. I have some point c, and all I can tell you is at that point, my derivative is either 0, so flat, or my derivative doesn't exist, meaning I could have like a corner or a cusp or something like that. Okay? Then it says that if my derivative changes from positive to negative at that point, so as I move from left to right, if I look a little bit to the left, if I'm increasing here, that means positive derivative, right? And then on the right side of C, I'm decreasing, negative derivative, then that must have been a little maximum, right? Do y'all see how we're going to use this? And then the next note says, if it changes from negative to positive, then it's the other way around. We have a local minimum. So if at some point C, I look to the left of it and I'm decreasing, and then to the right of it I'm increasing, then that obviously has to be a local minimum. And if the derivative does not change at that point C, then we don't have either thing happening. Let me give you an example of this one. Let's say at C, we have the derivative, maybe it's doing this. Look at that right there. What is the function doing to the left of that point? Is it increasing or decreasing over there? It's increasing, right? What's it doing to the right of C? It's still increasing. See, there's no change. I went increasing, increasing. There was no change in sign, which means that at that point we don't have a local max or a local min. Okay? Yeah, let's do some examples. Whoa. Let's do the quiz problem, but now we're looking at it from a different perspective. Remember, we moved into a different section. Remember last class I said we're going to talk about trying to find the max and mins on a closed interval? And then we're going to talk about finding the local max and local mins on an unclosed interval. That's where we are right now. So I'm going to give us the quiz problem, f of x equals 2x cubed plus 3x squared minus 12x plus 1. Okay? And I'm not going to ask you the question from the quiz. I'm going to ask you something else. I want you to find the intervals, intervals where f is increasing and f is decreasing. So this is two separate questions. I want to know where the function is going up, and I want to know where the function is going down. And then I would like to have you tell me or find any local maximums or minimums. All right, so the first thing we're going to do is pretty much the same thing we did with the closed interval method. We're going to take the derivative, we're going to find the critical numbers. So let's take our derivative. And on the quiz you should have had 6x squared plus 6x minus 12, right? Okay, and now what I want to do is set that equal to 0. So when I take this derivative and I set it equal to 0, I get 6x squared plus 6x minus 12 equals 0. And there's different ways you could solve this. I would just pull the 6 out. Like that. Oh, no, that's not 12. That's 2. And then just factor this. So plus 2 minus 1. And then you set these factors equal to 0. And remember, with the 6, we ignore it, right? Okay, so this just becomes x is negative 2 and x is equal to 1. So we have two critical numbers so far, right? So far. We also have to check, is the derivative ever undefined or not exist? Does this ever happen? Yeah, the derivative is quadratic, so there's no problems here, so nope. Okay. So in the quiz, this is pretty much what you did for the quiz, right? Except now what you did is you took those and you took the endpoints of the interval and you compared them all, right? We are not going to do that now. Because we're trying to figure out where this function goes up and where it goes down, right? So now what I'm going to do is, this is brand new, like we have not done this, all right? The next step is to take our critical numbers and draw them on a number line. Okay, so I'm going to take my critical numbers, draw them on the number line, and I'm going to make sure that I get them in order, okay? So make sure they're in the correct order on the number line. And by doing this, it's like we know what's happening here and here, right? What is the derivative here and here? What is the slope of the tangent line at these 2 points? 0, right? 0. What we're interested in is where's the derivative positive? Because that would tell us where we're going up, right? Where's the derivative negative? That would tell us where we're going down. This is where the derivative is 0. So I know what's happening here and here. I just don't know what's happening over there. I don't know what's happening in here, and I don't know what's happening over here. Make sense? So this is going to create a very natural partition of our number line into three separate regions, right? I have the region to the left of -2, the region in between -2 and 1, and the region to the right of 1. If I would have had 4 critical numbers, I would have put 4 things here, and then I would have had 5 regions, right? If I would have had 1 answer here, then it would be 1 number with 2 regions. In this problem, 2 critical numbers, 3 regions. And so what I have to do now is figure out what's happening with the derivative in each of those regions. So I'm going to go over here to this first region over here, and this is where you have some flexibility, you have some options. You get to pick any point you want to the left of this, whatever you want. So -3, is that okay with you? Notice I marked it with a little X here. That's just to remind me I'm grabbing a point here. -3 is the number I'm going to pick. I'm going to circle it just so you understand that, just so we don't confuse these two. That's a critical number. This is what we are going to call a test point. And then I have to pick a test point somewhere in here. 0, that's a good one. 0 is always a good one to pick. And then anything over here. 3, 2 would have worked. 10 would have worked. 1 billion would have worked. Anything to the right of 1, right? And now the very important part. You're going to take those, right? And you're going to do something with them. What are you going to do with them? Plug them into what? So if you plug,
I'm sorry.
I want you to think about what the difference between these two would be. If you plugged it in here, what would it be giving you as an answer? The y value. It would tell you how high the function is there, right? So if I plug -3 into that, it would tell me where I am up and down, right? If I plug that number -3 into this, what's it going to tell me? The slope of the tangent line there, right? And that's what we want to know, right? We want to know, is it pitched up over there or is it pitched down? So that test point needs to go into the derivative. That test point needs to go into the derivative, and that test point needs to go into the derivative to check to see if we get a positive or a negative answer out. Make sense? Yeah. Okay, so I'm going to do that now. I'm going to actually test the points. So I'll put up here, just so you remember, test points always into f prime, right? Always go into f prime. So I want to know what f prime of -3 is. I want to know what f prime of 0 is. And I want to know what f prime of 3 is. And what am I interested in the most? Whether or not it is positive or negative, right? That's all that really matters to me. Is it positive or negative? I really don't care too much about if it turns out to be like 8 or if it turns out to be 4. As long as it's positive, that answers my question, if it's going up or down. But for this, it's pretty easy to plug in here, isn't it? Later on, the problems are going to get more complicated. I may not actually plug them in. I may do something a little bit like shortcut. But let's just plug it in. So -3 in here, 9 times that is 54, right? I don't trust my arithmetic anymore. That's going to become a minus. So this one right here is minus 24, and then minus 12. And I believe when you put all that together, you're going to get a positive number, aren't you?
24.
Yep. So it's 24?
Yes, sir.
Is it? I believe you. No. 18. Okay. Yeah. It's positive, right? That's all that matters to me. Okay. So what that tells me is this. Over here, to the left of negative 2, my derivative is what? Positive. If the derivative is positive, what does that tell me my original function is doing? Increasing. So to the left of negative 2, I know that my original function is increasing. Pardon?
That's incorrect.
That's incorrect too? What is it?
It's 54, negative 18, minus 12.
Who told me 24 here?
Just use those numbers.
Look, I'm sick of this. I'm really getting sick. I'm going to have to take arithmetic seriously now. I really am going to have to. I went back and watched my video from the other day. I just posted it today and saw where I made the mistake. I put a negative twice for that. Remember the problem with the what was the problem?
Yeah, we messed up.
Not the highway problem, the farmer's pen one. I had put negative twice and turned it plus. It was correct up to that point. All right, let's start over. Okay, negative 3 into here. Negative 3 squared is 9. 9 times 6 is 54. 6 times negative 3 is negative 18. Minus 12. Right? There we go. So that's minus 20. So 30. 4.
Yeah, it's 24.
24. My God. It's still positive. My goodness. Okay. All right, I don't mind plugging in 0. That I can do all day long. And that means I have a negative number, right? And so the function is decreasing over here, right? And just remember, I mean, this is the derivative, right? This is information about the derivative. That's giving us information about the original function. I mean, technically, we're saying the derivative here is positive. The derivative here is negative, right? Positive derivative means function going up. Negative derivative means function's going down. And then last, if we plug in 3, 60. I'm just going to trust y'all, okay, because I don't trust myself anymore. Okay, so function is going up. And so that note we just had a second ago said that if we have a critical number c, and our function goes from increasing to decreasing, right? If we have a change in sign, the derivative went from positive to negative, then we will have to have what happening here? A local max. A local max occurs here. Can you see the hill? Okay, we have a hilltop, and then we have a local min at 1 because we have a valley. All right? So now we do this. We say, well, let's answer the questions, okay? So where is the function increasing? Let's first determine that. So here's my final answer because I've done all the work. My final answer is that f is increasing where? Yep, everywhere down there forever, all the way until we get to negative 2. Not negative 3, negative 2. So negative infinity to negative 2. Is that the only place? Union, where? 1 to infinity, right? So that's why I circle my test points. It's so I don't accidentally use them later as my interval. Like these things that are circled are only there for testing. When it comes to my answer, it's going to be either that or that. Okay, where is it decreasing? Negative 2 to 1. All right. Was that the only thing I asked? About increasing and decreasing. That was it, right? Then I asked for local max and min. So find any local max and min. So I know I have a local max. Where do I have a local max? When I plug negative 2 in. Into what? The original function. So if I plug -2 into the original function, not to the derivative, then I know that I will have a local maximum. So I still need to do that. I've got to plug -2 in there, and I believe that's where you get the 21 from. That's just like on the quiz. And then we have a local minimum. So what is the local maximum value? 21, okay? But you can look at this as being a point, right? The point is the point -2, 21. Like if you were to go to -2 up 21, that's a point on the graph, that's a local maximum. All right, what about local min? You plug in 1, and you should get -6. So that's like a point, that's the point 1, -6. Now, and are we saying that these two things are our absolute or global max or min in min? No, because we are not restricting this function to a closed interval anymore, right? And if you graph this, I'm not going to do it on the computer, but if you graph this, it does this. Okay, so what we have found is that point and that point. We have found where we have a local max and a local min. Okay, do you understand the basic idea? Start out with the function, find your critical numbers, take your critical numbers, create a number line, break it up, test points, test into the derivative, figures out up and down, and then put all that information together in an answer. Yeah? Okay, let's do a harder function then. Last class, I kind of got myself off on a tangent. We really didn't get to do any challenging functions. So today, we'll do some challenging ones. Should we jump right into the fire? Okay, let's jump right into the fire.
I mean, Game of Thrones is premiering this Sunday, so.
I actually have no idea what you're talking about, but I mean, I've heard of Game of Thrones, but if it was by me saying jumping in the fire, if that somehow relates to it, I don't know the relationship.
Yeah, Dragonfire, that's all I gotta know.
Dragon fire?
Yeah, just watch Game of Thrones, it's great.
Okay. I mean, it must be good. A lot of people like it, so. But I don't like a lot of things that people like, so maybe not. So let's see here. Same instructions here. Find where this function is going up and where the function is going down, and then find any local max and min values. All right. So we want to do the same exact process for this function. Now that is not a function that you see every day, right? That is, well, you don't see any functions every day, right? Just unless you're in math class. Yeah, so this is a weird looking function. So let's start by taking the derivative, right? Because we want to find the critical numbers. So the first derivative of this, or the derivative of this is, what are we going to use to take the derivative here? Just the power rule, right? We have two separate terms. We can do them one by one. We have x to a power, so power comes out. We subtract 1 from the power, right? We've done that way in the beginning. We had the power rule. So what happens when you bring 2/3 out and it hits the 5? It becomes 10/3. And then x to the -1/3. So you have to subtract 1 from 2/3, which gives you -2/3. And then you do the same thing on the second term. Bring that 5/3 out, hit the 2. You get another 10/3, don't you? And then this one is x to the, subtracting 3/3 from 5/3, you get 2/3. So there's our derivative. And now we get to set that to 0. Ooh. So when I set the derivative equal to 0, how are we going to do that? Right? I mean, so this is not like a little polynomial where you factor and it's not fun anymore. Yes?
If I had to speculate my next move, You're probably gonna take that negative 1/3 and flip it under.
That's exactly what I'm going to do. I'm going to take that negative power and drop it down. Is that what you meant?
Yes.
Okay, so I'm going to rewrite this as 10 over 3x to the 1/3 minus 10x to the 2/3 over 3. And I want to set that equal to 0, don't I?
You would like factor out a 10x to.
You could factor out a 10/3 from both of these, but you want to also pull an x?
Or,
I'm okay with you pulling an x, but I'm just not quite sure what x you would pull out. Because what do they both have in common? You could do an x to the 1/3, you could do that. I mean, there's kind of multiple ways of doing this. There's not just one algebraic way. You want to try it? You can try that on your own, see if we get to the same thing.
like when we were doing homework, I did like a different way.
Yeah, that's okay. That's okay. That's the great thing about algebra. It's not like you do it one way, I do it a different way. We're going to have different answers. If we both follow the rules of algebra, we should arrive at the same thing. Sometimes you go down a road algebraically and it becomes more complicated looking. So you just want to, if that ever happens, you might want to back up, try something else. Okay, I'm going to stick with this because I'm going to put these together with a common denominator. Okay, so if I could do a common denominator here, this one has a 3, that one has a 3, this has x to the 1/3. I'm missing an x to the 1/3 here. So I multiply x to the 1/3 on the bottom and the top, right?
What's great about that is that x is gonna turn into 1.
Yep, we're going to have the common denominator on the bottom, like this, right? And then what do these two become? X to the 1, right? X to the first power, because you add up the two exponents. So I'll have 10 take away 10x on top. And that must be 0, right? Go with me? Okay, now, does anybody remember?
Multiply the bottom with 0. You have to worry about the top.
You only have to worry about the top. If a fraction is ever 0, you only have to worry about the top, right? Okay. Now we do have a little, well, let's keep going. So this means that 10 minus 10x must be 0, and just solving that, you get what? X is 1. So x is 1. We have one critical number so far, right? All right, now, are we ready to draw the number line, or we got more to look at? We got a little more to look at. We have to consider the possibility that this derivative might be undefined or not exist. So let's consider that. Does this derivative ever have a problem? When what? If x is negative? Well, we're doing cube roots, right? Cube roots are okay. So let me back up. This right here, it's hard to look at that. I think it's hard for most people to look at that and just say, oh yeah, if you try and plug in this, you're going to have a problem. But from this step to this step to this step, do you agree this was just algebra, right? So look at that. That is the derivative, right? Is there something that would cause a problem? What? If x was what? 0, right? If x was 0, there would be a problem with that derivative, wouldn't it? It would be undefined. So we actually do have something happening here. X equals 0 is a place where we have something happening that's not good, right? The derivative is undefined. Now, we do need to check. Make sure, like these numbers, like you can plug these numbers into the original function, right? Like this thing may have had a domain, and maybe these numbers aren't even in the domain. But can you plug 0 in here? What does this mean, 2/3? Means square it and then take the cube root. So if I take 0, square it, and take cube root, that's 0. If I take 0, raise it to the 5th power, it's still 0, and take the cube root. Why doesn't 0 work here? Because what does this mean? Well, it means that, right? So if I plug 0 in here, I'm going to get 0 there, and it's division by 0. So that negative exponent is what caused the 0 to become a problem. where we didn't have negative exponents here, so it wasn't an issue. All right, now what? Number line. So number line, put these in order, make sure, let's see, 0, 1. That breaks up my number line to 2 pieces. Pick some test points, and these test points will go into the derivative, won't they? Okay, so my test point, something to the left of 0, -1. Something between 0 and 1. 0.5 or a half, that's, unfortunately, we can't get away from, can't use a whole number. We got to use something. So 1/2, and then something to the right of 1, 2. Yeah, let's go with 2. And those will go into my derivative, right? So I don't feel like plugging those numbers in here. I think that's going to be nasty, don't you? But, I mean, would you agree it would be kind of messy to plug those in there? So I really like this version of our derivative. I really like that. It seems super clean, doesn't it? So that's the one I'm going to work with here. I'm actually going to take this derivative, and I'm just next to it, I'm going to rewrite this, because I think it'll be really nice to work with that. And you know what? Let's change it to cube root of x, because that's what it is. All right? That's what this is. Remember, we're not setting equal to 0. We're just going to plug in now. So let's do this. F prime of -1. Okay, so what happens here? If we plug -1 in right here, we're going to wind up doing 10 minus -10, so that's 10 plus 10, that's 20 on top, right? 20. And then on the bottom, what? Oh, I forgot the cubed. That's what I heard y'all saying something. That's cube root, sorry. So what is the cube root of -1? -1, right? -1 times -1 times -1. So cube root of that, and then times 3, -3. And what do I care about here? Whether or not it's positive or negative. And in this case, it's negative. So we have a negative number here, and that means that over here to the left of 0, my original function is decreasing. And then I go and I plug in a half into the derivative. So I plug a 1/2 into here. So half of 10 is 5. 10 minus 5 is 5. So we've got 5 on top. And now this might be hard to do on my calculator, without a calculator, right? But what's the cube root of a half? Is it positive or negative? It's got to be positive, right? Do you all agree? The cube root of 1/2 would have to be a positive number. Because something times itself 3 times. If that's going to be positive, then it had to start off positive. So the cube root of 1/2 is positive, times 3 is positive. So do you agree the bottom is positive? I don't need the number. I don't actually need to get on my calculator and do it. Because 5 is positive on top, positive number on the bottom. This is positive, right? And so it goes, and my original function there must be going up. And then we plug in 1 to the derivative. And we get 2, sorry, 2. 2 goes in here, and we get a negative on top, right? So I stop caring about the numbers, okay? I really do stop caring about the numbers. Negative on top. What about the bottom? If I plug 2 in here, cube root of 2 must be positive, then times 3, still positive. So we get a negative over a positive, which is negative. So now that tells me that the original function goes down here. So almost every time I cover this in a Cal 1 class, students will ask me, can I just find the first one and then just just assume that they switch the rest of the way down? And the answer is you can't. Unfortunately, some functions will go down, down, then up. They won't just keep alternating. So you have to check each one. All right. Do we have any local minimums or maximums?
Max at 1.
We do have a max at 1. Do we have any minimums? We have a minimum at 0, right? It goes down then up. Down then up. So ready to answer the questions here. Where was our function increasing? Where was the function increasing? Increasing. Just 0 to 1. Between 0 and 1, you're going up, right? Where's your function decreasing? Negative infinity to 0, unioned 1 to infinity. So everything leading up to 0, everything past 1. Local max. Where is that happening? Where is it happening?
1.
At 1, right? So we plug 1 into the original function. The original function, right? So we plug 1 into this, and that should be a pretty easy computation, right? 1 to any power is 1. 1 to any power is 1. So this is 5 minus 2. It's 3. So we have a local maximum of 3, and then a local minimum. Where is that happening? At 0. And that's easy to plug into the original function, because that just gives you 0.
Can you draw a function where it wouldn't go like this? Like, how is it going to have a derivative of 0, or like where the slope is 0? And
Where the
not
slope is,
switch, not switch.
and not switch, I could do something like f of x equals x cubed. Okay, like this. So if I took the derivative of this, what would I get? 3x squared. Okay, if I set that equal to 0, what am I going to get? What's the only answer I get if I set that to 0? 0, right? So I draw a number line. Here's 0. I'd pick a test point here and here. So let's say I pick -1, right? -1 would go into here and become positive, right? So that means I'm going up here. And then I'd plug in +1 into here, and I'd still get positive. So see, it doesn't switch? Is that what you were asking? Okay, so you can see from the picture that what's happening is that our derivative here is 0. We have a flat tangent line. However, we are increasing and then still increasing, so there's not a local max or min here. Was that clarifies it? Okay. All right. Are we done? Oh, I was going to graph this on the computer and see if it can handle it. Sometimes the computer has some problems with these rational exponents, but I'm feeling pretty good that Desmos is going to do okay on this. Oh, the one from last time. What was the function? It was 5x raised to the 2/3 minus 2x raised to the 5/3. And my window's all messed up here. They need a little like zoom out button, just like zoom standard graph. There it is. There's your function. Kind of an interesting looking function, huh? So we found, where was our local max? We found this local minimum, right? We found that, didn't we? That was a local minimum, and it is from the picture. And then we found that point right there, which is our local maximum. All right, let's do another one. Let's take a look at this one first before we actually go after it. This one is x to the 2/3 times x plus 9. Okay? That looks kind of like the other one flipped over, doesn't it? You know what? That looks too much like the other one. Let's not do that one. I think the algebra and that's going to be too similar. I was trying to do one kind of like what was in the book, but I think we've covered that. I want to do something very different. Product rule, yes, you could use the product rule. I wouldn't, though. I would just distribute that through. And that's why if you do here to here, you can get x to the 5/3. Go here to here and get x to 2/3. It'll look just like the other problem. Okay, we'll do this one. I think we have enough time. We can probably get two more in. X times the square root of 9 minus x. All right, let's start out with the derivative, right? Because that's what we're going to need. Yeah, this is going to be a product rule. And we could force this in if we wanted to. Remember, what happens to something when you push it into a root? It gets squared on its way in. So we can either keep these separate and do product rule, or we can push it in. I'm going to just keep them separate and do product rule right here. So the derivative of this one is 1 times that, which is just this. And then plus, what's the derivative of this piece? 1 over 2 root minus x. Now chain rule times -1 times x. And that finishes off your product rule. So we had to do derivative of this, which is 1 times that, plus derivative of square root of something is 1 over 2 times the square root of the something. Chain rule says derivative of what's in here, derivative of 9 is 0, derivative of negative x is -1, and then finish off the product rule, you got to multiply by the first one. All right, let me clean this up. Root 9 minus x minus x over 2 root 9 minus x. So just put that negative x up on top, or actually put the negative out front here, left the 2 down there with the root. So that's our derivative.
And then you put 2 square root 9 minus x under the square root 9 minus x. Actually turn it to...
For a common denominator?
Yeah.
I will do that. Let me set it equal to 0. Okay, so I'm going to now take this, figure out when this is 0. So I set up the equation. Get a common denominator between these two. So look at that as being over 1. So we have to introduce the 2 root 9 minus x here and 2 root 9 minus x there. Sorry, I'm squeezing that in there.
And then correct me if I'm wrong, but I turned it to 2 times 9 minus x.
This root and this root together turns into 9 minus x, but you still have a 2 out front. So 2, 9 minus x, and then minus x, and then over the common denominator. And then that equals 0. Tired today? You tired? You look tired.